Good morning, everyone. My name is Yang Liu. I'm an associate professor in dynamics and control from the University of Exeter, UK. Today, I'm very excited to give you a talk on the locomotion of a vibrational capsule for lower GI examinations. However, it is very unfortunate that I couldn't give you this talk in person, but I believe we will have the chance to talk to each other in person in the near future. In this talk, I'm going to cover the background and motivation of this research. Then I will show you the working principles of our prototype. I will show you both standard and untendered vibrational capsules. In particular, I will focus on the locomotions of these vibrational capsules self-propelling in the intestine. In this talk, I'm going to cover both numerical and experimental results, followed by concluding remarks. As you know, capsule endoscopy is the technique to examine the small bowel and the colon. However, the passive capsule brings two major issues. As you can see from this video, it may stuck somewhere in the intestine, so operation is needed. Another issue is the position and the locomotion of the capsule is not controllable. So during the examinations, the symptoms might be missed by the passive capsule. Therefore, there are so many different groups developing different techniques to control the locomotion of the capsule. Our aim of this research is the same. We want to control the locomotion and position of the capsule during the examinations. However, we don't want to use external mechanism to bring the second damage into the intestine. So we want to develop a very smooth surface for the capsule, but we still can control the locomotion. Our prototype is simple. We employ internal magnets, and then we apply the either internal or external magnetic field to accelerate the magnets. Once the magnet is accelerated, it will impact with the main body of the capsule, and then the net force will overcome the friction in the intestine, so the whole capsule will progress forward. Then we switch off the magnetic field. The magnet will rebound back to its original position. Then we switch on the external magnetic field again. It will re-accelerate and impact the main body of the capsule. After repeating this procedure, our capsule can progress forward. We also can change the frequency of this vibration and also the amplitude of the vibration. And then we can control the direction of this capsule. It could move in either forward or backward. This is our first prototype. We developed 26 millimeters length, 11 millimeter in diameter. And we use this T-shaped magnets and helical spring to bring the magnets back to this original position. In the capsule, we have the constraints, forward constraints and backward constraints. So once the external magnetic field is applied, the magnets will impact with the constraint. By using this principle, we developed a tendered vibrational capsule. We put the coil inside of the capsule, and then we use a ball bearing to control the direction of this impact and vibration. So the magnets can impact in different directions. For this design, we can control the orientation of this capsule. We also demonstrate that in a curved tube. As you can see, for different frequencies and duty cycles, we have different average speed, and we demonstrate that on the X vivo environment. Then we develop these untendered vibration capsules, and this prototype is slightly bigger than the previous prototype. In this time, we use external magnetic field. We use a handheld controller to provide the external magnetic field for the internal magnets. As you can see from this schematic diagram, the clinicians will use the controller on top of the patient body to guide the capsule. And this is the demonstration in our column pattern. We also investigate the dynamics of the capsule during the progression in the column. As you can see, for different frequencies of this excitation, we have different speed for the capsule. So we can control the frequency and the duty cycle to control the speed of the capsule. What we are really interested in is the dynamics of capsule during the transition. Then we developed this mathematical model, and I'm going to just simply introduce this model here. What you can see from this schematic diagram, we have a capsule. Instead, we have this T-shaped magnet. And then these T-shaped magnets will be excited by the either internal magnetic field or external magnetic field, and then it can generate a force on the magnets. Then it may impact forward constraint or backward constraint. And then we can write the motion of these equations of this prototype. We have the first equation for the internal magnet, and then the second equation for the capsule. For the exciting force, here we use a harmonic excitation. We also can use a square wave excitation by switching on and off. In this model, we consider a column friction. And from our experimental studies, we believe the column friction is sufficient to express the motion of the capsule. And Fi is the interaction force between the magnets and the capsule. And we have some experimental comparisons between simulation and experiment. As you can see, we have forward progression for the capsule and also backward progression of the capsule. What we are really interested in the frictions from the intensities, the maximum frictions from the intensity is the resistance force from the circular fault or Hastro fault. The biggest issue when we self-propel the capsule is that we have to overcome this resistance force, and the capsule has to cross over the fault during the examination. So we have to extend our mathematical model. We have to consider this fault. It could be either the circular fault or the Hastro fault. I'm not going to give you details about this modeling process, but what I want to emphasize is the additional to our previous mathematical model of the capsule, we have this actual force. This is the resistance force provided the fault. And as you can see, this is the force profile during when the capsule contact with the fault and then cross over and then pass the fault. Then we want to verify this force experimentally. So we developed this experimental rig. As you can see, we have the intensity and also the circular fault. And then we use a mechanism to pull the capsule. Once the moving speed of the capsule is a constant, then the pulling force will equal to the resistance force on the capsule. In this case, we put a load cell here. So when this rig pulling the capsule, it will measure the pulling force. It is the same as the resistance force on the capsule. Then we have this comparison between experimental result and the mathematical model, also finite element result. As you can see, this is the experimental result. The black line represents the experimental result when it's moving on the intensity, and then it meets the fault, and the force increases dramatically, and then the capsule will climb up the fault. Climbing down the fault, we can capture all the forces during this procedure. What is really interesting here is the resistance force could become negative because when the capsule climbing down from the fault, the elasticity of the fault will give the capsule a push force. So the resistance force on the capsule will become negative in this case. However, experimental rig cannot capture this negative force because it is pulling force from the experimental rig. So it cannot be negative. Then we further examine the resistance force using a column flatten. We test the different force in different diameters, and then we measure the maximum force and then compare with our experimental result. So the red dots are calculated from mathematical model. So as you can see, the trend is very fairly consistent, which demonstrates our model is correct. Then we put our vibrating module into a commercialized capsule and then test it using a complete in-testing. As you can see, we can control the direction of the capsule in the in-testing. And in this case, we put the external magnetic field underneath the capsule. We also further validate its capability to pass the sharp angles in the column. As you can see from these two demonstrations, we have the capsule vibrating pass through these sharp angles, and indeed, these vibrations helps to passage for the capsule. We also demonstrate the capsule using a Poisson column. As you can see, we can control the direction of the capsule moving forward and backward. Finally, you may ask whether these vibrations will affect the image quality during the progression. Our experimental test shows that the vibrations did not affect the quality of the image. As you can see, the first row is the images without vibration. However, the quality of the camera is in low resolution. When we vibrate that in 1 Hz, 10 Hz, 20 Hz until 50 Hz, we couldn't recognize a big difference between these images. In this talk, I have introduced the vibrational and controllable capsule self-propelling in the lower GI. I have showed both standard and untended vibration capsules. In particular, we focus on the anatomy of the small intestine and colon, and what we are interested in is the maximum resistance force in the lower GI. We have shown you the locomotions of the capsule controlled by the frequency, amplitude, duty cycle of the vibration. Based on our ex vivo result, consider small intestine. Our examination may take about 30 minutes, and then for the colon, it may take 20 minutes. We also showed you the image qualities and the vibrations. There's no obvious difference for the images taken without vibration and with vibrations. At the moment, we are developing this technique at TRL3. We are trying to integrate everything into the capsule, such as cameras, sensors, and wireless connections. In the future, we are looking to develop this technique into a phase 2, which covers TRL from 4 to 6. This is the grant and awards for this project. And this is the team. I would like to thank my PhD students and postdocs, and also the clinical advisors to support this project. Finally, thank you very much for your attention, and I would like to receive your questions. You could contact me by email